start. In lesson 1, we had defined experimental probability as the total number of theoretical probability as the total number of successes divided by the total number of possibilities. Now, there's a difference, Steph, between theoretical and experimental. It's possible that you can roll a die and you can get 5 ones in a row. Is it likely? No. Is it possible? Sure. So the theory and the actual event often differ in real life. We introduced the notion of a tree, and we're going to take that a little bit further today. So lesson 2. Again, some more definitions and some techniques. Can you find the handout that says lesson 2 related events? First thing we want to define is a sample space. A sample space is a list of all of the possible non-overlapping outcomes of an experiment. For example, what's the sample space for a die? Rattle them off, Carson. Rattle them off individually. 1 or 2 or 3 or 4 or 5 or 6. And you notice I said or, there's no overlap. What's the sample space for flipping a coin? Heads or tails? What's the sample space for a deck of cards? Okay. Sometimes if it's a small thing, we might list the sample space. 6 of them wouldn't be too much to write out. Sometimes if it's a big sample space, like a deck of cards, we'll probably just try and visualize it. Here's an example. Example 1, one bill is randomly selected from the pot. What's the sample space? Well, traditionally we use a capital letter S for sample space. And traditionally we use the curly brackets from set notation. And we would say, well, 0 or 5 or 10. And I said to you the other day that, Reg G, we all have a basic, innate understanding of probability, but it's lousy. It only gets us so far. It does get us this far. What's the probability that a $5 bill is selected? How many $5 bills, Reg G, are there in the pot? Out of? Okay, that's correct. Example 2. Now we have 2 pots, pot A and pot B. Pot A has a 0, 5, and a 10. Pot B has a 5, a 10, or a 20. Section A says use a table to construct a sample space and use a tree diagram. Which is easier? We're going to do both. I prefer tree diagrams. I find them more visual, but they become unwieldy if you have 4 or more events. Your trees get really wide and yucky. So we're going to use a bit of both. And then we're also going to answer B, what's the probability that the sum of the 2 bills is $10? And already right now, if I asked you to take your guess to write down what you think the answer is, what are the odds that the sum of the 2 bills is $10? Most of you would be wrong, even though this is a very simple question. Like I said, Ragji, our innate sense of probability gets us so far, but not very far. Okay. If I was doing a table, draw the line down the middle, we do a table over here, I would go like this. Pot A can be a 0, a 5, or a 10. I draw kind of an L-shaped line like that. Over here I would put pot B, which can be a 5, a 10, or a 20. And I'm just going to pair them up, A and B. 0, 5, 5, 5, 10, 5. 0, 10, 5, 10, 10, 10. 0, 20, 5, 20, 10, 20. Holly, it wouldn't be wrong if you put pot A there and pot B there. Just be consistent. Don't start listing the top one first and then partway through your table start listing the one on the side first. Be consistent. Holly, how many outcomes are there? Count. Can we get there faster? How many outcomes are there? 3 by 3 is what? 9. You can also do a tree. I like a tree better for me. I find them more visual. My tree would look like this. Holly, how many outcomes are there in pot A? So there's going to be 1, 2, 3 branches to start out. Here's pot A, and the outcomes are 0, 5, 10. Trevor, you notice I went nice and wide because I know there's going to be sub-branches. I need some room. Then I have the B level right here, and it can be 5, 10, or 20, 5, 10, or 20, 5, 10, or 20. Does that make sense, Matthias? Okay. And Matthias, I would read this, for example, this branch here would be getting a 10 and then getting a 5. Getting a 10 from pot A followed by a 5 from pot B. I got every possible outcome listed there. B asks then, what's the probability that the sum is 10? Exactly 10. Well, in my table, it's pretty obvious. I think it's right there. In my tree, I think it would be that tree or that tree. That branch or that branch. Regardless, Ashley, how many successes are there? 2 out of 9. 2 out of 9. Which one's better? I like this, but a classic, a very common question is rolling 2 dice. 2 dice would have 6 branches followed by 6 branches on the end of each of the 6 branches. That's where the tree becomes too unwieldy. For dice, I would do a table. 1 through 6, 1 through 6, and list them all. There's 36 possibilities. Amanda, it takes you about less than 60 seconds, and then you have everything there. Deck of cards. Now, I've given you a picture of a deck of cards. You'll want to become a bit familiar with how a deck works. So, one card is drawn from a well-shuffled deck of 52 cards. How many cards? 1. We'll start doing multiple cards later, which are also equally cool. Use the graphical display of the sample space to find the probability of getting a red card. I'll call that the probability of capital R, and I'll do it in red. Why not? And I'm going to physically circle the red cards, which in my case are those right there. How many have I circled? And please tell me without actually counting them. How many have I circled, Amanda? 26 out of? Mr. Dueck? Yes, Amanda. Isn't that just a half? I know it's a half. Don't reduce your fractions, because I guarantee later on we're going to want to combine fractions. It's going to be, Amanda, really nice if they're all out of 52, because then I have a common denominator right away. Trust me. A jack. How about J for jack? I'll use black. The jacks would be that row. Ryan, how many? Out of? Okay. C, card that's not a jack. Now here's our notation. Ryan, we're going to write that as follows. Jack with a horizontal line above it. That means not a jack. Can somebody tell me the answer without counting up all of the cards? How did you get the 48? From? In fact, now really what you did is this. 52 out of 52 minus 4 out of 52 is 48 out of 52. You actually subtracted from 1, because the odds of something happening and not happening is 100%. Something happens or it doesn't. And 100% as a decimal is 1. All right. D. A red jack. Can you see in my diagram it's really the overlap? And this concept of overlap is going to be a really handy visual way for us to figure out what and means. What's both red and a jack at the same time? How many? It's a 2 out of 52. What about the probability that it's either red or that it's red or a jack. 26, and then, now you could do this a couple of ways. You could go 26 plus 4. Oops, I counted those two twice, so 26 plus 4 minus 2, or just count this. Now, you may not have realized it, Andrew, but we violated English by saying it this way. Anyways, you are right. It is 26 out of 52. Sorry? 28 out of 52. Sorry, you're right. 28 out of 52. Do you notice, Andrew, that actually includes that little chunk right there? You see, in English, if I say to you, I have a Mars bar here and a Milky Way bar here, you can have one or the other. You understand in English, it doesn't mean both. In math, or means one or the other, or both. It includes both the overlap. Always. Could be both. This is sort of a type of a Venn diagram. A Venn diagram is a picture of your sets and whether they overlap or not. Some terms for you. The complement. We're going to use that word, so you need to know that word. That's not an event. For example, if the event is a black card, what would the complement not black be? Red. If the event is an even number, what's the complement of an even number? Odd. Okay? And you can find them, if you can find one event, you can find the other event because they add to one. In fact, Tyson, what I usually use is this. The probability of an event not occurring is equal to 1 minus the probability of the event occurring. Often, it's instead of finding the odds of something not happening, it's way easier to find the odds of it happening and just go 1 minus that. Because something happens or it doesn't all the time. A and B, that's the event that both A and B occur, and it's this shaded in overlapping section right there. In our cards, it's where the two circles crossed, the two ovals crossed. A or B is everything inside this oval. It means one or the other or both. Example 4, turn the page. A black die and a white die are rolled. There's 36 possibilities. Katie, if they hadn't given me this table, I would have quickly drawn out this table. Takes about 60 seconds. You write 1 through 6 along the top, 1 through 6 along the rows, and then quickly list them. We're going to have the following events. Event A, the sum of the two dice is at least 9. Event B, the black die is 1 less than the white die. Use the sample space to find the following probabilities. So I'll do event A in red. I'll do event B in black, since it says black die and white die. So red, I'm going to circle all of the ones that are that add to at least 9. Looking at this, Holly, isn't it going to be this whole bottom corner here? That's going to be what adds to at least 9? How many? How many have I circled? Itzel, count. Count carefully. Out of? Did you use the fundamental counting principle? I hope you went 6 choices, 6 choices. Ah, see, that's why we always do the combinatorics unit before we do probabilities. The event B is the black die is 1 less than the white die. Now, looking at this table, Katie, I had to think about it for a bit, but it looks like they're listing the black die first and followed by the white die, because this right here says 1, 2, 1, 2. So where the black die is 1 less than the white die is I think that little diagonal right there, isn't it? Yeah. Sabrina, how many? Out of? Yep. Ah, now let's get to the more interesting stuff. What's the probability of A and B that the sum of the two dice is at least 9, 9 or more, and at the same time the black die is one less than the white die? Can you see it, Matthias? How many? What's the overlap? Yep. No? Just count how many? 2 out of? Yep. Yep. See it? These a Venn diagram where you circle, very visual. I can see the overlap. It's where they actually overlap. A or B. Holly, that means one or the other or both. You know what? That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You know what? That's going to be... Right? Steph, what about not A? And can you do it without counting? Can you tell me what the probability of not A works out to? Look here. What's the probability of not A? Yeah. Amanda. No, yes, we gotta be able to do this. Okay, ready? This is key. Yes! It's the complement, isn't it? 10 out of 36, 26 out of 36. No need to count. Okay? Great shortcut. In English, now you notice I don't even know what not A means. I can calculate it. What does it mean? In English, what would the event not A represent? Cassandra, can you read to me up here, what did it say that A represented? So what's the opposite of that? In English. I'll give you a hint. The sum of the two dice is... Huh? Right? At least 9. What's the opposite of at least 9? At least 9 means 9 or more. What's the opposite of that? Less than 9. It helps if you can translate it into English, because then you can start to think about what it means, especially for card questions. What's the opposite of a jack? Not a jack. Oh, 48 of those. Example 5. If each of the 13 outcomes in this sample space is equally likely, find. So here's a Venn diagram, a lovely Venn diagram. What's the probability of A? Well, first of all, it's going to be out of 13, because there's 13 events, it says. 13 outcomes. How many of those outcomes are inside event A? 4. How many are inside event B? 5. How many are not inside A? Now you can do it two ways. You can count or you can complement. 9, did you count or did you do a 13 minus 4? But by the way, for what it's worth, 1, 2, 3, 4, 5, 6, 7, 8, yeah. How many are not B, Andrew? 8. Nice. How many are A and B at the same time? Ragjit, what's the overlap? How many are A and B at the same time? What's the overlap? Right there. See it? 1. Now, Ragjit, here's what you answered, actually. I'll come back to you. How many are A or B, which means one or the other or both? 8. And do you see what I mean by those? That would be that section right there, right? Not A and B. Now, I can get it by using the complement. Katie, what would it be? What's the opposite of A and B? What's the complement of that? 12 out of 13. As a picture, what we would be talking about, Katie, would be this section, or that section, but not the... how many are not overlapping? not A or B. Again, I can get that using the complement 5. Where is that in the picture? Ah, that group right there. Now, by the way, another word they'll use for this is neither A or B. That's the neither group. They don't belong. No friends. Don't fit in. Lesson 3. Continuing on with fun stuff. What we really want to talk about a bit more, Ragji, is what you led us into earlier, the concept of OR. Lesson 3, the event A or B. And I'll give you this lesson in a nutshell. OR means add minus the overlap. OR means add. OR means add the overlap, although often there won't be any overlap. When do you add probabilities? Situation number 1. Each of these 13 outcomes is equally likely. Find the following probabilities by counting the outcomes. Can you fill in the first 4 on your own, please? I'll do them up here, but count and fill in what you think the answers are. And is the overlap is what, Cassandra? 0. That would be like, what are the odds of being heads and tails at the same time? 0. What are the odds of being a red card and a black card at the same time? 0. What are the odds of being a red card and a king at the same time? Oh, some overlap, because some kings are red. We have a fancy word for that you need to know. We say that these events are mutually exclusive. Why? No overlap. Well, actually there's a better mathematical explanation. The probability of A and B, that's the official math definition. If and is 0, they're mutually exclusive. And actually, sometimes they'll need to tell you, but usually you'll be able to figure it out. What are the odds of rolling an odd number and an even number? Or an even number? They're mutually exclusive. Can't happen both at the same time. What are the odds of rolling an odd number or a 3? Some overlap. You can be odd and 3 at the same time. What I want you to notice here, Steph, is can you see a relationship between these top 3 numbers? What? Can you say it mathematically? I think what you're saying is this. Is that what you're saying? What you're really saying, Steph, is I think OR means to add. If they want OR, what I'm really doing is I'm adding them together. Let's compare this with situation number 2. So here's another Venn diagram. Can you fill in the first 4 again? This one's got some overlap. Be careful. Can you fill in the first 4 again? Actually, did you get 4 out of 13, 5 out of 13, 8 out of 13, 1 out of 13? We say that these are not mutually exclusive. Why? Well, mathematically, it's because the probability of A and B is not 0. It exists. You can be both at the same time. There is some overlap. But here's what we've been leading to. Itzel, Can you see some way that I can get this number from these numbers? Can you see some way that I can get an 8 out of 13 from these guys? Anyone? Steph, what? This is the official OR formula. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, minus the overlap. And I actually remember, this formula is on your formula sheet, Matthias, but I remember it in English, remembering the card question that we circled last lesson, where you would have been counting the middle section twice, so you have to subtract it. I just think OR means add minus the overlap. By the way, Steph, that equation works up here too. I could have put a minus the probability of A and B right here, because what was the probability of A and B? 0, wouldn't have made a difference. This is the works every time. This is the specific for mutually exclusive. Okay? The addition law. So the probability of A or B is the probability of A plus the probability of B minus that. Oh, or if they're mutually exclusive, then the and part doesn't matter. You guys have those equations on the previous page. You can just copy them out, but I'll show you. You get these on your formula sheet as well. On your student reference sheet, on your formula sheet. There's the complement definition sitting on your formula sheet. There's OR. Having said that, Trevor, although I give you the formula, I myself hardly use it. I like visual tools. I tend to fall back on trees and Venn diagrams to which the answer pops out. Show you what I mean. So we are going to use the equation here to show that it works, but we're going to use Venn diagrams as well. Here's our deck of cards. This is our Venn diagram. One card, how many cards? One card is randomly drawn from a deck of cards. Right here. Okay? We're going to define the following events. The event S, the card is a spade. The event R, the card is red. The event F, the card is a face card. It says identify the events S, R, and F on the sample space. I'll do spades in black. You can just circle in pencil. Unless you have multicolors, go ahead. I'll do red cards in what color would make sense for red cards, Itzel? Oh, since I got that, why not? And I'll do face cards because it's a color left in green, which would be Jack, Queen, King, these guys. Can you see now which of these events are mutually exclusive, which of these events have no overlap? Which ones? Event S and R, event S and F, event R and F. Which ones are mutually exclusive? Which pair, there's only one pair, has no overlap? Can't be a spade and red at the same time, right? Could you have figured that out on your own without a deck of cards in front of you, Cassandra? I hope so. Some of the basic ones we can figure out. Now, it says, determine the following probabilities directly by counting outcomes. I'm going to show you that although you could, although the Venn diagram is nice, for most of these, if you're reasonably familiar with a deck of cards, you don't need the picture in front of you. So S was spades. How many spades are there in the deck? How many did I circle? I know that there's 13 out of 52. How many red cards are there in the deck? I know that there's 26 out of 52. How many red cards are spades at the same time? Can't happen. What would can't happen be as a probability? 0. How many cards, what are the odds, what's the probability if you're picking one card of getting a spade or a red? It's 39 that I've circled. But can you see I could also have used the formula, that plus that minus the overlap. In fact, I could have gone, this is the same as the probability of S plus the probability of R minus the probability of S and R, which is 13 out of 52 plus 26 out of 52 equals 39 out of 52. The second one. Well, what's the probability that there's a spade? 13 out of 52. What was the probability of the face card? How many face cards did I circle? If I don't have the deck of cards in front of me, I go, well, let's see, Jack, Queen, King, and 4 suited. You know what? How many face cards there are? 12. Right? Not 4, Tyson. 12. 3 in 1 suit times 4 suits. Jack, Queen, King times fundamental counting principle, right? 3 choices for a face card, 3 choices for a suit, 12 choices. How many face cards are spades? 3. I can figure that out because I know what a deck of cards looks like. By the way, I think if you look where I circled up higher up in the page, I think there's 3 overlapping between the face cards and the spades circles, yes? S or F. Now I can get there by counting, but for what it's worth, I think it's going to be 25, take away 3. It's going to be... Why do we have to take away 3? Because if you count, if you just go 13 plus 20, sorry, if you go 12 plus 13, you've counted this guy twice. So you subtract it once. As an equation, it's probability of S plus the probability of F minus the overlap, which is 13 out of 52 and 12 out of 52 minus 3 out of 52 is... By the way, Amanda, see why I told you don't bother reducing your fractions? You're going to want a common denominator, trust me. I know this is 1 out of 4, but who cares? So, Amanda, that's how the formula works. Again, I'll be honest, I know it, and you can hear, Steph, how I've learned it, not actually as the equation. I know OR means 1 plus the other minus the overlap, which is, to me, easier to wrap my brain around. I tend to fall back, though, on this, the Venn diagram, specifically for something like example 2. Example 2 says there are 30 students in a class. Excellent. 16 students surf the internet, and 10 students use email. Of these students, 6 do both. What's the probability that a randomly selected student in the class surfs the internet or uses email? This was typed up in 2001 because now the answers would be 100% and 100%. But still, let's just go with the numbers that we have here. How would I know to use a Venn diagram for this one? How many categories are there? 2, internet or email? That's a good hint that this is a Venn diagram question. So although solution A says use the formula, I'm going to say, nuh-uh. I'm going to draw a little rectangle here and 2 big ovals with some overlap, like that. And I'm going to call this internet and this email. I'll call them I and E. And when I'm filling in a Venn diagram, what I'm always interested in filling in first is the overlap, the middle, the both. How many are both according to this question? 6. All of you put a little 6 right there. How many students surf the internet grand total? according to this question, Holly. 16. I'm not going to put a 16 right here, though. Why not? Because I've already got 6 in this circle. What am I going to put right here? And that's how many kids only surf the net but don't have an email address. See it? How many kids email? Grand total. How many only email but aren't into surfing the web? Oh, how many kids neither surf the web nor have an email address? How many are outside of both of these ovals? How many kids are there in this class grand total? 30, and right now I got 10, 16, 20. You know what? Gotta be. The reason I like a Venn diagram also now is any question they ask me, Matthias, is staring me in the face. What are the odds that a kid doesn't surf the internet or email? 10 out of 30. What are the odds that a kid only has an email address? 4 out of 30. What are the odds that a kid surfs the net but doesn't do email? 10 out of 30. What's this question asking? What's the probability that a randomly selected student surfs the internet or uses email? Or means one or the other or both. I'm not going to use the formula here. I'm not going to go add together minus the overlap. I've got this all. I've taken care of it all already. The total is 20. It's 10 plus 6 plus 4. I don't need to subtract the overlap here. I'm not using the formula. I'm using a Venn diagram. It's when I don't have a Venn diagram in front of me, when I just know the individual odds, I have to use a formula. And you could already use this to solve some interesting questions, like example 3. Wilma the Web Whiz submits bids on 2 web design projects. After her first interview, she figures she's got about a 70% chance of getting the first project. In the second interview, she figures, I got about a 50-50 chance of getting the second project. She figures she's only got a 25% chance on getting neither. Find the probability that she gets, and there's a bunch of questions. Shannon, are they asking me more than one question here? Yeah. Have they given me percentages in the original question? That's some clues that a Venn diagram is your best approach. Okay? You could do this with a formula, but it's yucky. I'm going to draw a great big Venn diagram like this. And it's going to have project 1, project 2, and overlap. Read the question very, very carefully. Did she tell us the odds of her getting both of them at the same time? Did she tell us the overlap? Did she tell us and, Carson? No. But I said to you, I always start filling my Venn diagram in with the and I'm going to. I don't know what it is. I'll put an X there. Okay? What are the odds of her getting the first project, Carson? What am I going to put here? Not a 70. Oh, Carson, I thought I'd have to walk you through it. Talk to me, Carson. What? Because didn't you go 16 minus 6 to get the 10? 70 minus X. Okay. Carson, what are the odds of her getting the second project? 50. 50. What are the odds of her only getting the second project? 50 minus X. Oh, and Nathaniel, she did tell us one more thing. She told us, what are the odds of her getting neither? Where's that going to go? And then we're going to be clever one more time. I know the answer that I have to get if I add this number and this number and this number and this number. If I add together every possibility, what are the odds of every possibility happening? Always, as a percentage. Huh? 100%, or 1 as a decimal, 100%. Let me say that again. If I add that number to that number, to that number, to that number, that has to add to 100%. Has to. that okay, Katie? Oh, look, 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 look. A couple of your x's cancel. That's kind of nice. Gather like terms, add the numbers. I got 70 plus 50 plus 25. What is 70 plus 50 plus 25, please? 145. And there's also minus x that drops down. Oh, I don't even need a calculator for this. Holly, in your head, 145 take away what? Works out to exactly 100. What does x have to be? Did you say 45? You'd be right. So now I go running back to my Venn diagram, and I go like this, Holly. That's a 45. Oh, what number really appears in here, Carson? Thank you. Right? Oh, and what number appears in here? 5. Oh, and there. Now I've got my Venn diagram filled in with actual digits, numbers. Now I can answer any question they throw at me. A says both projects. Probability of 1 and 2 is how I would write that. What are the odds of getting both? You see it, Andrew? Too slow. Yeah, it's staring right at you. No need to go to a formula. It's the overlap. Good. Of at least one. Now that means one or the other. Or you know what that means? That really means 1 or 2, because we said in math, or means one or the other or both. Trevor, what are the odds of getting 1 or 2? Yep, could have gone 100 minus 25 if you're really lazy, or add those 3. 75%. Make that a better 5. Hey Sabrina, what are the odds of her getting only the first project? Now I would write that like this: 1 and not the second. That's how you would write only the first. Can you see it? Which of those ovals is only the first but not the second? That's not part of our we're not using. Don't use this anymore. 25, isn't it? Yeah? I'm not sure you guys, right? That's this section right here. How big is it? 25. That's one, but not both. %. D, only one, but not both. Can you see it, Itzel? Really? No? Folks, here's getting 1 or 2. Get rid of both. What are the odds of getting only one but not both, Itzel? 30. Right? I'm sorry. I'm not sure you guys are reading these right. It's staring out at us. 30. Venn diagram. Don't need to go to a formula. I can use a formula if I need to. There's ways to use that. Or means one plus the other minus the overlap. Yeah, I like a Venn diagram. Question, Amanda? No? Okay. So I like this question. I like this question. I like this question. On your test, I'm going to give you one where I don't tell you the overlap. Put an X there. Subtract your way out. Figure out what X has to be. Fill in all the numbers, Sabrina, and then just read carefully. What's your homework? Page 428 from the workbook, number 8. You just write this down at the bottom of the page first. And then from page 434, number 2, 5A and C. 6, number 7, but use a Venn diagram. You can do it with a formula if you really want to, but use a Venn diagram. And then 8, 9, 11, and 12. Go to your page and I'll add it there. Two 5AC, 6, 7 using the Venn, 8, 9, 11, and 12.